Good morning, everyone. Welcome to the session 9 of Engineering Mechanics and Strength of Materials. In the last class, we are discussing about volumetric strain, bulk modulus, and relations between the elastic constants with the help of Poisson's ratio and problems on that. Okay. So, what is meant by volumetric strain? Volumetric strain is nothing but when the material is subjected to three mutually perpendicular direction forces, it undergoes change in volume. When the material is within the elastic limit, the ratio of change in volume divided by original volume is known as volumetric strain. Correct? And what is meant by bulk modulus? K. It is denoted as K. Bulk modulus K is equal to ratio of direct stress to the what? Strain. Direct stress to the volumetric strain, that too. Because it is applies in three mutually perpendicular direction forces, then it undergoes change in volume. That's what bulk modulus is, ratio of direct stress to the volumetric strain, and it's denoted as K, and it should be within the elastic limit. Next, there are three elastic constants like E, C, K. E is equal to what? Young's modulus of elasticity. It is normal stress to the longitudinal strain or linear strain. And shear modulus C, which is equal to what? Shear stress to shear strain. And bulk modulus K, which is equal to direct stress to volumetric strain. And we have Poisson's ratio mu is equal to ratio of lateral strains to the longitudinal strain. Right? We need to establish the relations between those constants. So relation between E C mu is equal to what? E is nothing but Young's modulus of elasticity. E is equal to 2C into 1 plus mu. 2C into 1 plus mu. Right? And then E is equal to 3K into 1 minus mu. And E is equal to 9kc divided by 3K plus C. These are the relations between elastic constants. Okay. And we discussed the problems on that. Let me move on to next topic, session 9, temperature stresses. Okay. When the material is subjected to or experienced change in temperature, it undergoes change in dimension. When the materials are spaced at a close spacing, it experiences change in temperature, then automatically the stresses will induce. Okay. For example, see, we are having two cells or materials. Here. See, you can see over a span length, and it is interconnect with the stress relief arch here. What is this arch? See, the animation itself is showing whenever there is a change in temperature, it undergoes expand or contract. Due to expansion, what happens? There will be a stress will be induced without this stress relief arch. So that's why in every road deck slam, there is a gap. We can see that. So that gap, what it indicates? It is a gap for what? There is a change in temperature, and it is undergoes a expansion and contraction. Due to overcome the effect of temperature stresses, we are giving a gap between them. Likewise, here also the two materials, we are not provided with a stress relief arch. Automatically, the material will experience the temperature stresses and it will be get damaged. So for that reason, we need to study about the effect of temperature stress. Okay. Next, thermal expansion. Okay. So the material change size when the temperature is changed. We all have known it is a known factor in the atmosphere itself. For example, I can give you best example for this. The door in the winter season will stick to the frames. Will stick to the frames. In the summer season, it will free to rotate. It will free to move. Why that is happens? Why that is happen? In the atmosphere, the winter season, the moisture will come and the temperature of the material will also less. It will absorb the atmospheric moisture and it will expand it. The same thing when the expansion occurs. What happens? It will stick to the frame when we move forward and backward direction. The same door will going to be get shrinked. Get shrinked. Did you observe that? So due to shrinkage, it can be freely move and rotate. What is that effect? It is automatically temperature change. This temperature change, the materials also changes. How it is changes, it is expanded or contracted, and it is also depends upon when the free expansion is prevented, then it experiences a temperature stress. Then it is experiences a temperature stress. Okay. This is the bar of length L and it is subjected to a normal temperature. There is a normal temperature T initially. Over a period of time, it is get expanded. This L final. The temperature is more as compared to this. When T final is greater than T initial, how it will change in length? How it will change in length? L final minus L initial divided by L initial. That is the change in length, correct? Which is given by alpha L to T final minus T initial. Alpha is thermal coefficient of expansion or thermal coefficient of linear expansion, and L is the original length, and T final is the temperature at the final stage, and T initial is the temperature at the initial stage. Okay, so this is the alpha L. Alpha is nothing but thermal coefficient of expansion or thermal coefficient of linear expansion. L is the length of the member, and T specifically we can use it as what? Temperature change. Change in temperature. Okay. Okay, next. The most structured materials expands when heated in accordance with the thermodynamics law. Okay, so that is strain is equal to alpha into T. Alpha into T, where strain is linear strain and alpha is the coefficient of linear expansion. T is rising temperature, that is for a rod of length L, and if the temperature increases by T, the extension delta L, that's delta L, change in length is equal to alpha L into T. See, this is the same relation. The T is substituted between T minus T final minus T initial. Alpha is thermal coefficient of linear expansion. L is the original length of the member. So that is the change in length. That is what? Change in length of the member due to what? Change in temperature. Change in temperature. Okay. Next, for different coefficient of for different material, how it is the coefficient of thermal expansion will be changed. Let's see. The materials are given like polymers, metals and ceramics. See, always the thermal coefficient of linear expansion is expressed in terms of per degree centigrade. So usually all the values are in terms of associated with 10 to the power of minus 6 per degree centigrade. All the thermal linear coefficient of expansion will be in the order of 10 to the power of minus 6 per degree centigrade. Okay, so how it is rises? The polymers having a more values, ceramics having a less value. Ceramics having a less value. Why does alpha L generally decreases with increase in bond energy? Polymers have a high bond energy. Polymers have high bond. Okay, so next, polymers have larger alpha values because of weak secondary bonds. Primary bonds are more, but it's a weaker secondary bond. It's a weaker secondary bond. Here, steel material. Can you see? This is the most important for civil engineering. Steel we are using for reinforced cement, concrete, steel bars. Its value is 12 into 10 to the power of minus 6 per degree centigrade. We need to consider while designing our structural member. So what is the thermal coefficient of linear expansion is 10 to the power of minus 6 per degree centigrade. How much? 12 into 10 to the power of minus 6 per degree centigrade, and other materials values are given. So usually the material thermal coefficient of expansion is high for what? Polymers, and it's low for ceramics materials, and for a metal is in the average range. We can see that. For why, what is the reason for polymers there is a high alpha L or thermal coefficient of action is secondary bonds are weak in nature, so that's why coefficient of thermal expansion is high for this. Okay, understand? Now move on to next slides. Temperature stresses. The thermal expansion is equal to thermal coefficient into change in temperature into original length. That is already we have explained in the earlier slide. Alpha into T2 minus T1 into L, where alpha is coefficient of thermal expansion or coefficient of linear thermal expansion. So its value is first is 12 into 10 to the power of minus 6 per degree centigrade. T2 is the final temperature, T1 is the initial temperature, and L is the length of the bond. Okay, yeah, it is given T. We are using T final minus T initial is equal to T. Then when the case 1, yeah, there are two cases will come. Why the two cases will come? When the material allowed to free to expand, there is no stresses induced. When the deformation or the expansion is prevented, then automatically the stresses will induce. That's we need to find out here. When the deformation is completely prevented, strain is equal to change in length or expansion divided by original length. Et strain is equal to alpha into T. So change in length divided by original length. Change in length is equal to, we have already formula, alpha L T divided by L is equal to alpha T. Next, when the end supports are yield by delta, that is L alpha T, change in length is greater than delta, then what happens? Temperature strain expansion is prevented over the original length. ಎಷ್ಟು ಎಕ್ಸ್ಪೆನ್ಷನ್ ಪ್ರಿವೆಂಟೆಡ್ ಆಗಿರುತ್ತೆ ಅದಕ್ಕಿಂತ ಕಡಿಮೆ ಇರುತ್ತೆ, ವಿಚ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ವಾಟ್? ಎಲ್ ಆಲ್ಫಾ ಟಿ ಮೈನಸ್ ಡೆಲ್ಟಾ ಡಿವೈಡ್ ಬೈ ಎಲ್. ಸೊ ದಿಸ್ ಈಸ್ ದಿ ವೆನ್ ದಿ ಸಪೋರ್ಟ್ಸ್ ಈಲ್ಡ್ ಬೈ ಡೆಲ್ಟಾ, ಏನಾಗುತ್ತೆ ಅಲ್ಲಿ ಎರಡೂ ಕಡೆಯಿಂದ ಸಪೋರ್ಟ್ಸ್ ಇರುತ್ತೆ. ಆ ಎರಡೂ ಕಡೆಯಿಂದ ಸಪೋರ್ಟ್ಸ್ ಇದ್ದಾಗ ಇಟ್ ಈಲ್ಡ್ಸ್, ಇಟ್ ವಿಲ್ ಅಂಡರ್ಗೋಸ್ ಸಮ್ deformations with conjunction. So that is given by L alpha T minus delta divided by L. Okay, next we need to discuss some problems on these temperature stresses. Okay, I'll read out the question. A copper rod 15 mm dia and 800 mm long is heated through 50 degrees Celsius. How much? 50 degree. A copper rod 15 mm dia, 800 mm long, and is heated through 50 degrees Celsius. What is its expansion delta L, and when it is free to expand? Suppose the expansion is prevented, gripping both ends and supported by both ends. Find the stresses, its nature, and the force applied by grips when the grips don't yield. ಅಲ್ಲಿ ಏನಾಗಿಲ್ಲ, supports will not be get healed, and they have given modulus of elasticity E is equal to how much? 1.25 into 10 to the power of 5 Newton per mm square. Okay, write the given data. Okay, so alpha is also given 18 into 10 to the power of 5 into 10 to the power of minus 6 per degree centigrade. For what? Copper. Coefficient of thermal expansion ಎಷ್ಟಿದೆ ಕಾಪರ್ಗೆ? 18.5 into 10 to the power of minus 6 per degree centigrade. Data are given. The diameter of the copper bar is 15 mm, length of the copper bar is rod is 800 mm, and temperature T is equal to 50 degree. It is heated through 50 degree. You can understand. E is equal to 1.25 into 10 to the power of 5 Newton per mm square, and alpha, there is a linear thermal expansion, is 18.5 into 10 to the power of minus 6 per degree centigrade. Okay, now what we need to find? Expansion, change in length, stress, what is the stresses occurs, And the nature of stress, whether compressive or tensile, force exerted by the end support, force exerted by the end support. These are the parameters we need to find using those above data. Okay, now thermal expansion, we have the formula alpha T L. Alpha is given, T is given, L is given. Substitute and you get answer 800 is the length of the bar. T, that is 18.5 into 10 to the power of minus 6. They have put it in decimal points. And 50 is temperature change, is equal to how much? 0.74 mm. Sorry, how much? 0.74 mm. Okay, next temperature stress. Ft is equal to what? Stress is equal to what? E into strain. Young's modulus of elasticity into strain. Strain is nothing but what? Alpha into T. Okay, so we have all the values. Substitute here. 0.00000185 into 50 into 1.25 into 10 to the power of 5. How much it is? 115.625 Newton per mm square. The temperature stress. We got the answer for our questions. First question and second question. Next, nature of stress is compressive because it's a gripping at the both ends, and area of the bar is given pi d square by 4, 177 mm square. Next, force gripped by grip stress into area. The force we need to find out. Stress into area, how much? 20.465 kilonewton, 20465 kilo newton. Now answer expansion is 0.74 mm. Expansion ಎಷ್ಟಾಗಿದೆ 0.74 mm. Stress ಆಗಿದೆ 115.625 Newton per mm square. And next, nature of stress is compressive in nature, and the force exerted is 20465.6 newtons. These are the answer for our questions. When you are solving the problem, read the questions carefully and write the unit properly. So without the unit, your answer is wrong. Please remember. Without an unit, your answer is wrong or incomplete. So you will lose the marks. Remember always, you should use the proper units for the parameter you are finding. And you should read the questions once, twice, is no problem, and write the given data and what you need to find out. Then write the formulas. Okay, and you solve and try to practice the use the calculators. Let's move on to next topic. Okay, working stress and factor of safety. Working stress and factor of safety. Working stress. Let's we discuss about first working stress. What is meant by work? What is meant by work? Work andre ಏನು? ವರ್ಕ್ ಅಂದ್ರೆ ಕಂಡೀಷನ್ ಅಂದ್ರೂ ಅದು ಯೋಗ್ಯವಾಗಿದೆ ಯೂಸ್ ಮಾಡಲಿಕ್ಕೆ. ಒಂದು ಮೆಟೀರಿಯಲ್ ವರ್ಕಿಂಗ್ ಇದೆ ಅಂದ್ರೆ ಏನಂತ ಅರ್ಥ? ಅದು ನಾವು ಯೂಸ್ ಮಾಡಲಿಕ್ಕೆ ಯೋಗ್ಯವಾಗಿದೆ ಅಂತ. So there are different types of methods of design of the materials we are having. First one is ultimate load method, and second one limit state method and working stress. These are the three methods we are following since design of the structure member is initiated through IS methods. Here the working stress we are using is nothing but in order to find the factor of safety. Here design is separate. Why we are using in this topic of strength of material, particularly simple stress and strain, just for to find the factor of safety. Working stress is nothing but the point at which the material is loaded, just below the ultimate load, before failure, up to which the material is designed. ಅಂದ್ರೆ ಒಂದು ಮೆಟೀರಿಯಲ್ ಮೇಲೆ ಹಾಕಿದಾಗ ಅದು ಮ್ಯಾಕ್ಸಿಮಮ್ ಎಷ್ಟು ಲೋಡ್ ತಗೊಳುತ್ತೋ ಅದಕ್ಕಿಂತ ಸ್ವಲ್ಪ ಜಸ್ಟ್ ಬಿಲೋಗೆ ಲೋಡ್ ಹಾಕಿದ್ರೆ ಅದು ಎಷ್ಟು ಮೆಟೀರಿಯಲ್ನ ತಗೊಳುತ್ತೋ ಆ ಮೆಟೀರಿಯಲ್ನ ಹಾಕಿ ಡಿಸೈನ್ ಮಾಡಿರ್ತಾರೆ, ಆ ಲೋಡ್ನ ಹಾಕಿ ಡಿಸೈನ್ ಮಾಡಿರ್ತಾರೆ. ಅದಕ್ಕೆ ನಾವು ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್ ಮೆಥಡ್ ಅಂತ ಹೇಳ್ತೀವಿ. just below the ultimate andre ade last. For example, we are having this water can, we are forcing this. How much load can possible to withstand by this water bottle, that we can able to find, and we are loading up to that limit, ultimate limit before failure ಅಂದ್ರೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಎಷ್ಟು ತಗೊಳ್ತೋ ಅಲ್ಲಿ ತನಕ ಹಾಕ್ತೀವಿ, ಅದು ಹಾಕಿದ್ಮೇಲೆ ಫೇಲ್ ಆಗುತ್ತೆ. ಆ ಫೇಲ್ಯೂರ್ ಲೋಡ್ಗಿಂತ ಕೆಳಗಡೆ ನಾಟ್ ಫೇಲ್ಯೂರ್ ಲೋಡ್, ಅಲ್ಟಿಮೇಟ್ ಲೋಡ್ಗಿಂತ ಕೆಳಗಡೆ ಎಷ್ಟು ಹಾಕಿದಾಗ ಆ ಲೋಡ್ ಎಷ್ಟಿರುತ್ತೋ ಆ ಲೋಡ್ನ ತಗೊಂಡು ಡಿಸೈನ್ ಮಾಡಿದ್ರೆ ಅದಕ್ಕೆ ನಾವು ಹೇಳ್ತೀವಿ ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್. ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್. ಓಕೆ, ಅಗೈನ್ ಅಲ್ಟಿಮೇಟ್ ಲೋಡ್ ಇಸ್ ಡಿಫ್ರೆಂಟ್, ಫೇಲ್ಯೂರ್ ಲೋಡ್ ಇಸ್ ಡಿಫ್ರೆಂಟ್. ಅಲ್ಟಿಮೇಟ್ ಲೋಡ್ ಅಂದ್ರೆ the material will undergoes a change in stress and strains when we load it. We cannot load it only up to elastic limit. Always. The design methodology will be changed depending upon the type of structure. Normally, the framework structure are designed by using limit state method. Okay. Up to yield point, we are using the loads. Ultimate load method is different. Working stress method is different. Okay. So you should understand what is meant by working stress now. Okay. That load. And why the factor of safety is required here for a material. What is meant by factor of safety? That's we need to know. Factor of safety is nothing but the material we are using for any activities of constructions or whatever it is to carry the load. We are assuming it is within the elastic limit. Stresses are within the elastic limit, and stress strain relationships are linear, and the material is homogeneous and material is isotropic. These assumptions we are having. Without these assumptions we cannot design. Why the factor of safety is used? These assumptions may not be fulfilled always in the site according to the site conditions. There may be variations with material property. So that's why what we need to do, we give some inputs to carry the load, without fail. Safety is the prime important for our civil engineers. So that's why what we need to do, we need to give some extra safety through what? The material properties. So that's why we are using the word factor of safety. Always you should remember that. Factor of safety is nothing but what? We are giving extra strength, extra material property, whatever you can imagine. That factor of safety is nothing but we are giving some extra inputs not to make the structure safe. I will give it an example. Okay, let's discuss that. Material is stressed to point much lesser than the ultimate strength. Such stress is called as working. Yeah, that is what ಅಂದ್ರೆ ಅಲ್ಟಿಮೇಟ್ ಲೋಡ್ ಎಷ್ಟಿರುತ್ತೋ ಅದಕ್ಕಿಂತ ಸ್ವಲ್ಪ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಕಡಿಮೆ ಹಾಕಿರ್ತೀವಿ, ಅದಕ್ಕೆ ನಾವು ಹೇಳ್ತೀವಿ ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್, ವಿಚ್ ಇಸ್ ನಾರ್ಮಲಿ ಈಕ್ವಲ್ ಟು ಸ್ಟ್ರೆಸ್ ಅಟ್ ಪಾಯಿಂಟ್ ಪ್ರಪೋರ್ಷನಲ್ limit. Okay, next, the ratio of ultimate stress to the working stress is known as factor of safety. Correct? Factor of safety ಅಂದ್ರೆ ರೇಷಿಯೋ. ಅಲ್ಟಿಮೇಟ್ ಸ್ಟ್ರೆಸ್ ಯಾವಾಗಲೂ ಏನಾಗಿರುತ್ತೆ, ಜಾಸ್ತಿ ಇರುತ್ತೆ. ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್ ಏನಾಗಿರುತ್ತೆ, ಕಡಿಮೆ ಇರುತ್ತೆ. ಅಲ್ಟಿಮೇಟ್ ಸ್ಟ್ರೆಸ್ ಡಿವೈಡೆಡ್ ಬೈ ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್ ನಾವೇನ ತಗೋತೀವಿ, ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಅಂತ ತಗೋತೀವಿ. ಹಾಗಾದ್ರೆ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ವ್ಯಾಲ್ಯೂ ಇಸ್ ಆಲ್ವೇಸ್ ಗ್ರೇಟರ್ ದ್ಯಾನ್ 1. ಯು ಶುಡ್ ನೋ ದಟ್. ಯಾಕೆ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಗ್ರೇಟರ್ ದ್ಯಾನ್ 1 ಆಗುತ್ತೆ? ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಅಂದ್ರೇನು? ಅಲ್ಟಿಮೇಟ್ ಸ್ಟ್ರೆಸ್ ಡಿವೈಡ್ ಬೈ ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್. ಅಲ್ಟಿಮೇಟ್ ಸ್ಟ್ರೆಸ್ ಅಂದ್ರೆ ಏನಾಗುತ್ತೆ, ಜಾಸ್ತಿ ಇರುತ್ತೆ ಯಾವುದಕ್ಕಿಂತ, ವರ್ಕಿಂಗ್ ಸ್ಟ್ರೆಸ್. ಹಾಗಾಗಿ the value of factor of safety is always greater than 1. Okay, understand? And then the factor of safety, the material of load is different, material is different and for load is different. Okay, we are using different factor of safety, different types of load, and we are using different factor of safety for different types of material. For example, for concrete we are using 1.5 as a factor of safety, and for steel we are using 1.15 as a factor of safety, and we are using for a soil it's a minimum 3, and for a black cotton soil or clay type of soil we are using more factor of safety, even 4 5, and we are using for a wind load is different factor of safety. The factor of safety will be changed according to the type of parameter we are using, either material or load, whatever that is. Okay, ultimate stress or yield stress divided by design or working stress. Okay, next. The ratio of ultimate load to allowable load is known as factor of safety. Whatever that is, you call it as a strength or you call it as a load. So that's also called as factor of ultimate load divided by working load. Can also be defined using yield stress is criterion. Factor of safety is also defined as ratio of yield stress to allowable stress. Yield stress to allowable stress or working stress. Next, factor of safety is also defined on the basis of ultimate stress to the ratio of ultimate allowable stress. Ultimate stress to the allowable stress. Factor of safety is also defined based on what? Ultimate stress to the allowable stresses. Okay. Why I am giving so much important for the finding a factor of safety is nothing but we should remember our material whatever we are using, the strength what which is having, we are not subjecting that much of load when we are designing. Still we are considering the higher values because of what? For safety purpose. Because of what? Safety purpose. Okay. For any structure if we are designing, we are designing it to limit stored method. Limit state is nothing but what? Limit up to which the material will not be stressed. For that load we are using. If we are loading beyond that limit, then what happens? The material or structure will be failed. So that's why we are using the word, the factor of safety. We are using the factor of safety here. Okay, understand? Next, note. The ultimate stress is used for material, example concrete, which do not have well-defined yield point, or brittle material which behave in a linear manner up to failure. Yield stress is used for other material, example steel with well-defined yield stress. Yeah, this is the different property. See, for a reinforced or cement concrete, we are using two material. One is concrete, another one is a steel bar. Okay, concrete is a brittle material and steel is a ductile material. In this ductile material is showing well plotted yield graphs. The stress strain relationships are linear and it will give very good yield stress, well yield stress. Okay, so that's why we can use that material having a less factor of safety. For example, comes to brittle material, it will not having well defined yield point. Well defined yield point. So brittle material always behaves in a linear manner with up to failure point. Okay, stress at failure divided by stress when loaded. Factor of safety. See, you should understand. You should understand this. Stress at failure and stress when the loaded. ನಾವು ಲೋಡ್ ಮಾಡೋದು ಯಾವಾಗಲೂ ಫೇಲ್ಯೂರ್ ಲೋಡ್ ಅಲ್ಲ, ಒಂದು ಸ್ಟ್ರಕ್ಚರ್ ಮೇಲೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ದಿಸ್ ವಾಟರ್ ಬಾಟಲ್ ಐ ಶೋನ್ ದಟ್ I have this nearby. This material if we are loaded, what happens? We can load only the carrying capacity. For example, treated as it is a column. This column will be loaded only up to its capacity, not its capacity. It's a working load. It's a working load, but its failure load is different and it's much more than this working load. So factor of safety is nothing but its failure ultimately, maybe 10 time or 100 time, whatever that is, it will carry at failure point. But working load may be, it's an example, it's a 10 load, 10 kilometer is nothing but 10 ton. Okay, understand? So that's why factor of safety value always more than 1. You should remember that. Should remember. Okay, thank you. We'll end up with the sessions.